switching. But there are many other providers and who have a legacy infrastructure in place, and they have been just providing IP services. So they have come a long way, and that IP services is not something they would like to drastically change and make it as an MPLS core to provide some of these labeled services. So they would like to use the existing infrastructure that they have, and they would like to build on top of it. So that's one of the advantages that this particular feature or this particular functionality provides. And at the same time, they would like to enable additional services, as I said, L3VPNs or multicast VPNs on top of that. So it should be quite transparent for enabling any new services. Now, from a MPLS-based core that exists today, these kind of services are enabled, and the same feel is what is required when I have a plain IP core. I don't have any MPLS or anything in my core networks. It is just doing an IP lookup and forwarding. And pretty much most of the routers are meant to do that. And bringing in an MPLS switching functionality to it was something from a hardware perspective or from an implementation perspective brought in a lot of challenges for the vendors. But if I have a box which can do good IP routing, I think it's worth utilizing that capability and bring in these additional services. And another view is we had multiple backbones, with IP core, and we used just the IP core for our internet access, and we built in another core. We said, oh, this is going to be my ATM based, or it's going to be my label-based networks. I would like it would be better if I can have a single network which could be just a plain vanilla IP and integrate all of these services. So what we call as a converged common IP backbone. That view actually it kind of brings in a little bit less overhead for the provider, because he's looking at one single network. Earlier it was all spread across for providing multiple different services. Now he's in a position where he can combine all of this together. Now I say simplify network operations, but I believe you guys doing it on a daily basis, so it's not as simple as it sounds. It has its own challenges, but one variable we are eliminating there is, I think from a knowledge base or from an expertise perspective, I think we have been doing well with IP, and bringing in MPLS into the play, we are kind of added an extra layer of knowledge that the maintenance folks would be requiring. Now that is somewhat we are minimizing here. But still, there is the concepts, still demand a good knowledge base. Now, when I talk about secured infrastructure for service integration, so here, it's always a belief that once I have an IP core, I'm prone to a lot of attacks, and it's very risky to have a plain IP core. I would like to have some kind of an encryption built into it, or some kind of a secured mechanism built into it. So keeping that in mind, there are various ways one can achieve that, because with MPLS core we always used to say that we have a domain where we are allocating these labels, so I know what I'm allocating and what I'm expecting. So there is very less chances for somebody attacking it very easily. Once it comes to IP, and there are more chances. So to eliminate that, there are techniques that are used today where we can encapsulate the packets that are going out in the core as well as towards the edge in a manner that it is less prone to attacks. So there are details in terms of how this is achieved. So just to give a more detailed view of this particular concept that I'm referring here. So 2547 was what we all are aware of, which was always used for layer 3 VPNs with MPLS-based layer 3 VPNs. So here that's obsolete, and we are having 4364, which is what is a common RFC that defines how L3 VPN services are available today. And the same concept is still used, because there we are using BGP as multi-protocol BGP as one of the key components to drive the end-to-end reachability and prefix exchange and labeled BGP and things like that. All that concept still holds good, even if I'm using an IP core. Now, even though I'm talking about an L3 VPN services, I'm not differentiating between V4 or V6. So that's something to keep in mind. In all of my previous presentation, when I talk about L3 VPN, I'm just assuming that it should be so transparent that I should be able to forward whether it's V4 prefix coming in from my edge CE routers, or it's going to be a V6 prefix that's coming in from my edge CE routers. I should be able to handle both of them transparently, and pretty much most of the functionalities from an implementation perspective, as well as from a deployment perspective, I think with whatever we learned from MPLS-based core, it still very much holds good with an IP core. There has not been major changes, but I think the key factors that is there today is two approaches. So one is MGRE tunnels, so the multi-point GRE tunnels. That's one mechanism of encapsulating an IP packet with the GRE header, and then use my regular 4364 standards features that exist and transport my packet over the network. That's one method. There's another option, which is what we call using L2TP v3. So layer 2 tunneling protocol has been there all along. It's not something new. V3 has been enhancements that has been added. Now what it brings in is brings in a flexibility in forwarding this IP in IP kind of a concept for L3VPN services. So my focus of this discussion is going to be mainly with respect to L2TP v3 tunneling mechanism, because that's something unique, and I will talk about the advantages that it brings in. So MGRE is another option, which is also again widely accepted, but I'll focus on the L2TP v3 part. So when we talk about tunneling, so always the concept comes, so I need to define a tunnel, and that tunnel has to be span across all the PEs that exist in the router, and that's an overhead from a service provider perspective, because now he has to manually configure each of these tunnels, and wherever the traffic needs to be destined, he has to force the traffic to go over the tunnel. Now if I have a site which is having 20,000 locations worldwide, and imagine the complexity that the service provider has to deal with if we are talking about doing a static tunneling configuration, right? So what this talks about is using the BGP capabilities where I can define a single tunnel on my one PE, which can be used to talk to all the multiple PEs that exist in the network. Because I'm already doing an IBGP peering in my regular L3VPN, where I do need to have an IBGP peering between PEs. So already I'm doing IBGP peering. Now all I need to do is an additional capability of exchanging this tunnel information that I'm configuring in my PE routers, and that can be exchanged across all my PEs. Now that's what this bullet is talking about. Instead of manually configuring all the tunnels, I'm relying very much on BGP to do the next hop reachability for my tunnels. Now the packets that are going to go out from my PE, the Ingress PE, is going to be encapsulated with L2TP v3. So the next few slides goes by in detail as step-by-step operation as to how this is achieved. So I'll just go through some of this here, but we'll go through in detail in following slides. So there is something called as a session ID and a cookie value. So I talked about encrypting or protecting the packet that goes out on the wire. So session ID and cookie are one of the parameters that exist in an L2TP v3 header. So if I'm going to encapsulate a packet coming in from my CE router to go towards my core routers, I'm encapsulating L2TP v3 header, so that has this cookie and session ID values. This cookie value is something that is exchanging between my peers. So I would have told my neighboring peer router that this is the cookie value that you're supposed to expect from all the packets that I send it to you. Now when that packet reaches to the remote PE, he will do a lookup and he will match. Okay, this is the packet coming with the right cookie value that I have been told from the neighbor. Now based on this cookie value, then I'll make a decision whether I should handle this packet or I should drop it. Now it's an optional field, so obviously if once I have this field integrated in the packet, then it'll occupy the space as a packet that is going out on the wire, so the packet size will be looking as bigger, but it can be varied in the sense I can have a 0-byte cookie or a 2-byte cookie or 4-byte or an 8-byte cookies. Those things are configurable parameters. So one can, as an end user, we could configure this and say, okay, let's have an 8-byte cookie as a standard in my entire network, or a 4-byte cookie as a standard in my end-to-end network, depending upon how susceptible the network could be. And there is another additional details in terms of why give a cookie value as a static between PE1 and PE2. Make it more dynamic, means make it more of a rollover. Periodically, every 3 hours once, or 5 hours once, or 10 hours once, make it change so that the neighbors are updated with newer cookie values. So I'll have more details on that. So BGP is what I refer here is being used as a standard to exchange this Encap header information from one PE to another PE. So this is how the overall network would look like. So you would have at the bottom of the slide, you could see there is an IP transport network. So This is a network which would like to have L3VPN services or V6 services enabled on this. So we would have these three boxes that we are showing here can be considered as PE routers, the provider edge routers. And they are there is an IGP running internally. So obviously you know how to reach each other. And that's doing a regular IP lookup, or IP transport is what exists. Now on top of that is what we are calling it as a tunnel overlay multi-access network. So what that means is I'm going to define one static tunnel on my edge routers. On all of them you can see a small boxes there. So they are pretty much one tunnel that I have defined. And I'm not indicating who will be my source and destination for that tunnel. Source is derived from BGP. So BGP would know that the loopback ID of the PE is the source for this tunnel, but destination is not defined for this. Because every PE would be exchanging this tunnel information, so each one knows who is the other tunnel. So there is no specific destination IP addresses for these tunnels. Now, from the way it looks, the tunnel network will be responsible for switching the VPN traffic. Means any customer traffic that comes from the remote CEs and it comes to the local PE. Now once I do the lookup and I'm supposed to forward the packet to the core, now that responsibility of redirecting this packet to go over the tunnel is coming from this multi-access network. Now the bottom diagram that we have, which is the IP transport, is mainly responsible for reachability between the PEs. So PE1 to PE2, how to get to is what this IP transport provides, whereas traffic from one CE to another CE, how do I reach? That information is provided by the tunnel overlay network. Okay, so going a little bit in detail, so I have a few slides which further talks about a comparison with the generic terminologies and details that we are already aware of from an L3VPN MPLS based. So here, what I'm referring about is a packet that came in from a customer router to the provider router, and I'm doing a lookup, and I'm now supposed to send this packet to my next hop or a remote CE router. Now to do that, what are the additional things that's being done? So the lookup is done, and that would tell me who is my next hop PE. Now once I know the next hop PE, I now have to redirect this packet to go over with the tunnel. Now the packet that goes out now will be looking something like this. So if you look at the top, it's called as a tunnel IP. It is nothing but a 20-byte header, and there is a protocol ID, which is what we call the L2TP v3 protocol ID. And then the source IP address and the destination IP address. So the first source IP address and destination IP address here, it refers to the reachability of the PEs. So the PE1 is where is my source IP address, and PE2, the loopback ID of PE2 is where I'm supposed to reach. That's the destination IP address of the remote router. Now the session ID and cookie I just explained. I'll go through that in detail. And then there is this label information. So this is the BGP WRF label. This is again as per the regular BGP extensions, that the labels were exchanged between PE1 and PE2 for the customer prefix. That's the label that I'm imposing. And at the bottom is where is my customer's payload. So if you look at it, it's a customer's payload, BGP label, then there is an L2TP v3 header and the tunnel IP. Now as this packet goes to the core routers, pretty much the lookup is done on this top header, which is what I'm calling as a tunnel IP. So the lookup is done on source IP address and destination IP address, and I just switch the packets based on the top tunnel IP header. Now once it reaches the remote destination, which is my PE2 as an endpoint, that when I do the lookup, I come to know that that packet belongs to me, and I do a further lookup into, I need to look into the label and then do the forwarding to the Egress PE routers. So this is what exactly we see when a packet leaves from an Ingress PE routers going towards the Egress PE routers. Okay, so a little bit more in terms of this particular payload here, which I talked the L2TP v3 header part. So here if you see the session ID and cookie values is a part of the L2TP v3 header, and so cookie field is around a 64-bit, and it's a value that is associated for every data packet that I'm going to send out to the remote PE, and it is associated with the session ID. Now the cookie values, as I said, it is a variable values, means it's an optional, it's exchanged as a part of my BGP updates via my multi-protocol BGP, and that 0 bytes or 4 bytes or 8 bytes is again depends upon how protective I am of my network. Obviously, once I have an 8-byte, you're going to use up your resources in the network. But pretty much this brings in more advantages, because now I have a 64-bit random value. Now to guess the 64-bit random value for any attacker, it's going to be a big challenge. Hence, most of the providers do go with 8-byte as the cookie value. Another parameter which I said earlier was the cookie rollover. I think that's one of the key items that exist today, where these cookie values need not have to be statically configured. So these are, once I define a tunnel on my PE router, a local cookie value is generated and it is exchanged across all my networks. And I need not have to keep that value constant. I can configure a parameter which is called as cookie rollover, where I could configure it saying, okay, after 5 hours, do the cookie rollover, right? So then the cookie rollover happens and every PE is now exchanged its new cookie values. So this is something which is widely accepted because we don't want to keep a standard fixed cookie values. So I just gave a bullet here. Mark Townsley, I think one of the leads who has presented a lot of details on this L2TPv3 in previous presentations. He talks about how many years it would take for somebody to guess a 64-bit cookie value if that packet goes onto the network. Okay, so I think this slide would be the best one to give you a detail as to what I was been talking about. So comparing pretty much to the regular MPLS as a transport that exists today, most of them are using this mechanism where MPLS, which we call LDP or RSVP, is enabled in the core. And now this diagram talks about 3 PE routers, so PEA, PEB, and maybe the top one is PEC. And you have these edge CE routers, which is where our enterprise customers are home to. And now there are colors associated with it. I hope you guys can see that. So CEA and CEB, being as they are part of the same enterprise or the same site. Now, what this would require here is there is an LSP that has been already established between PE and PEB. So this is how in an MPLS network we would have an LSP. It's established between PE and PEB. And now using that LSP, that is basically used for me to achieve the reachability between PE and PEB and provide the labeled path. Now along with this, I have PE and PEB in an MP-IBGP sessions. So there is an IBGP session that runs between these and which is responsible for carrying my customer prefixes, the prefixes that CEA has sent to PEA, and now that needs to be forwarded to PEB. Now multi-protocol BGP would be doing this as a part of VPN v4 or a VPN v6 address exchanges. So those prefixes would be reaching to the remote PE. Now that part where learning the routes from CE and forwarding those routes as a part of MP-BGP to the remote CE, all that part still remains the same. So that's what I'm calling it as untouched, in the sense, if I'm using an IP core today, that functionality would still remain the same. There is no difference whether it's an MPLS core or as an IP core. Now, what needs to be changed is, let me talk a little bit on the MPLS part of it. So if a traffic now, I need to send traffic from CEA to CEB. So packet comes to PEA. Now I do a lookup to figure out where I need to send this packet. The next hop for that packet I already know via BGP, so I need to forward that packet to PEB now. Now when the packet is supposed to go out, in the case of MPLS transport, I would be imposing an IGP label, that is a label to reach the next hop router in the path, or along with that I need to impose what we call the BGP label or the WRF label. So this is the label that the PEB would be looking up and forwarding the packet to CEB. Now, I need to change that because I'm not having any MPLS as a mechanism here. I'm still having an IP in my core. So what I would be doing for this case is I would be changing that, and the packet will be encapsulated with an L2TPv3 header. So the one which I showed in previous slide, that is what is the packet that PEA would be sending it to PEB. So the packet that goes out from PEA would look like it's having a source IP address as PEA, destination IP address as PEB. That is going to be in the top tunnel IP in the previous slide which we saw. And then there is a session ID and cookie value which is already been exchanged. And then I have the BGP WRF label, which is exactly same as what in an MPLS transport case as well. And then comes the customer payload. So that's what I meant by saying untouched in the first part, because that's the regular MP-BGP mechanism. It has nothing to do with whether I use MPLS transport or an IP transport. Only change would be is how I would forward the packet going out from PEA to PEB. So I think this particular slide, kind of refreshes our regular MPLS L3VPN v4 concepts. So it's 4364 is the standard that would define how I would exchange the customer prefixes between the PE routers with the next hop address information. Ingress PE, has already an LSP established because we are running LDP in the core. So we have an LSP which is established between PE and PEB. Now Ingress PE resolves the customer prefixes within the WRF table, and it would impose an IGP label with the VPN label and a customer payload. Now the traffic that is destined over the core uplink interface is all MPLS enabled. That's what we have LDP already running. Now the core P routers, once this packet reaches the core P router, now they are not doing an IP lookup here because they are getting a labeled packet. So they would be doing a label lookup and then either swapping that label with a new label or pushing or popping a particular label depending upon the configuration and the network topology. Now Egress PE is where I would be doing the label lookup because that's the final place I would have got the label information, and then that would further I would be doing IP lookup to forward the packet onto the egress interface. Now this is a flow which is talking with respect to the MPLS based core. Now similarly, if I am changing this and I'm having an IP core where my P routers or my core uplinks are not MPLS enabled and it's a regular IGP that is present today, then what would be the difference? So the difference here is, from a BGP perspective, I would have done all the initial work of exchanging the customer prefixes and the labels, BGP label that is associated to it. That part still remains the same. Ingress PE can reach the Egress PE through the IP core because I have an IGP that is running, so I know the reachability. Now, only additional difference that here that the Ingress PE has to do is where Ingress PE has to now resolve these customer prefixes and point to an L2TPv3 tunnel. Now that is the additional difference that you could see, which was not existing in the case of an MPLS core. So Ingress PE would be putting an L2TPv3 header on top of the customer IP packet that I got and forwarding it. So the Ingress PE would impose tunnel IP or L2TPv3 header plus the VPN label plus the customer payload. Now traffic will be drained over the tunnel. So the packet that is going out now will be looking something like the tunnel IP plus VPN label plus customer payload. Now, as the traffic moves along, now the lookup has to be done on the tunnel IP, and there is no involvement of any LDP here. So that's what this P router would be doing. So the P router, which is in the path, now it will be doing a standard IP lookup because my tunnel IP is a regular 20-byte IP header, which has the IP address of from where the source packet came in, and it has the destination IP address of the Egress PE. Now it knows how to reach the Egress PE, so that lookup will forward this packet to the next hop, which could be next another P router that exists. Now, so pretty much the standard holds good, where the core P routers need not have to be aware of any VPN prefixes because there is no lookup done with respect to the VPN prefixes. Now here is the advantages that I was referring, because pretty much the core P routers could be the same P routers which the provider has been using all along for his legacy IP services. So he's not doing anything extra here, means he's not enabling any MPLS, or he is not doing any further investment in terms of making sure I have a hardware which is capable of doing MPLS label switching. I could still use my existing IP capable P routers that existed for forwarding regular internet traffic or any other services that I had enabled. So he would just use the same, and it will be a regular IP lookup for these P routers. Now, once the packet reaches the Egress P router, now this is where the lookup will be done, and that will tell me that this particular packet belongs to me because the destination IP address belongs to this particular PE router. Now, along with this, the additional two important things that it has to do is it has to verify is the session ID and the cookie values. These were what I had exchanged as a part of my BGP session exchange. So as a part of that, I would go and make sure that the packet that I got is matching the cookie and the session ID that I had received earlier as a part of my BGP exchange. If that matches goes through, then, which we call, I'm calling it as an admittance check here. So if it matches, then only I will go and further look into the packet. If there is a discrepancy here, if I got a spoof packet and it has a cookie value which is not matching with what I was told earlier, I will drop those packets. Now, once this cookie and once these packets are matched, all of this information, I would further look up and find out what is this BGP label. So based on the label lookup, I would know which is the egress interface I'm forwarding the traffic to. So that is what is the last couple of bullets here it talks about. So the BGP label lookup will result in a WRF and its associated outgoing interfaces. Now tunnel IP, L2TP v3 header, and the BGP label. Since I have done all of this, I would be stripping off all of this, and now I am left with an IP packet, which is what it's supposed to be forwarded to the Egress CE router. Now, I think the slides further, actually this particular slide would explain all of this in detail. So this slide kind of gives a summary as what I was talking all along. So in an encapsulation behavior, so what I'm saying here is on the Ingress PE, where I'm supposed to encapsulate this packet which is going out to my IP core, I would be doing a simple IP packet lookup because this is coming from my customer site. I do an IP lookup, and that destination of that packet tells me which is the Egress PE I'm supposed to go. And since I know the Egress PE, now I'm supposed to put a L2TP v3 header to it. So I would be associating a VPN label and a tunnel encap, or the L2TP v3 encap to it. And then I forward this packet out to my core. Now on the decapsulation, once I got the packet, I do a lookup onto the tunnel IP that tells me that the packet belongs to the Egress PE itself, and then it does the admittance check for session ID and cookie, and then it would forward the packet based on the label lookup that it was already allocated. So this is how a typical flow happens from an end-to-end, from an encapsulation behavior and the decapsulation side in a service provider network. Now, the core routers are transparent to this. They are doing a regular IP forwarding and an IP lookup. So here is, I think this particular slide will kind of goes a little bit more in detail and kind of reiterate the same information that I was passing along. So if you look at, there are two parts to this network. So PE1, PE2, PE3 are the real PE routers which exist in the service provider network, and kind of at the bottom I'm talking about the IP network. So what I'm referring there is it just kind of gives you a view of how the reachability that exists for these PEs. I might have multiple PE routers in the middle or multiple hops to reach my Egress PE routers. I know the reachability of it. So that's what the first bullet talks about. There's a remote endpoint is routable through IGP. So PE1 knows how to get to PE2 or PE3 and things like that. Now once I know that, I would have configured what I call as a tunnel or a tunnel template on PE1 and PE2 and PE3. And once I have this tunnel defined, now that's what I'm exchanging between my IBGP sessions between all these PEs. So as a part of that IBGP session exchange, I'm exchanging the session ID and the cookie values, and also I know the reachability of each of these PEs. Now that is the second part, and then the third one would be is I got prefixes from my customer sites onto my PE1. I would be forwarding those traffic, those prefixes via my BGP, which could be a VPN v4 route exchange or a VPN v6 address family route exchange. I would be forwarding those prefixes from PE1 to say PE2 or PE3, depending upon from which site all of this belongs to. So similarly, so PE3 would be receiving VPN v4 and v6 via BGP. So this slide is kind of giving you from a control plane perspective. So what I mean is there is no forwarding involved here. How the end-to-end setup is built once the forwarding starts happening. Now this one is it clearly demonstrates that there is no MPLS in the core here, and it is pretty straightforward to get this setup as well. So from I think this slide just go ahead and gives an example, typically how in a service provider network today it is done. So the slide to the left, I think the left side of the slide, you talk about CE1 talking to PE1, and there are core P routers, and then there is a PE2, and then there is CE2. So CE1 to PE1 is where my customers' access links are terminating, and I would be running the regular protocols that are supported. Like either it could be BGP or OSPF or RIP or static, or if it is V6, there is another set of protocols that are supported. So that's what I'm running from a PE1 to CE1. And the prefixes like 152.12.4.0/24 as one of the prefixes that this CE is advertising will be now installed at PE1 in one of the VRF tables. I hope you guys are aware of the VRF virtual routing forwarding tables. So these are the tables that are built, which are kind of configured between PE1 and CE1. I would have defined a VRF interface, and I'm making it as a unique. Means for all the other customers who are home to the same PE1, I would be defining different VRF interfaces, and the routes will be populated to their corresponding tables. So in this case, let's say it's VRF1. That is where all these prefixes that I'm learning from CE1 would get installed. Now from PE1, now I need to forward these or advertise these prefixes to PE2. Now before I do that, couple of things that should have already been up and running in this network. So one thing is I would have defined the tunnels, I would have exchanged the tunnel information between PE and PE2 already, and then I would have had this address family VPN v4 as the capability exchange for BGP between PE and PE2. That should have been already done. And I know how to get to PE1 and PE2 via my regular IGP. So I have an IP core, so I know how to get to PE1 and PE2 through ISIS or OSPF as a regular IGP. Now these things were already done by the provider and it is available. So the prefixes that CE1 advertised to PE1 now gets forwarded to PE2 via the VPN v4 address exchange. So what this VPN v4 pretty much does is it kind of brings in uniqueness to the prefix that I'm receiving from each of these CEs. I would have multiple CEs. So to make it unique, I'm associating, as you look from the VPN v4 update here, so you could see it is associating the RD value, the route distinguisher that is associated to every VRF. So route distinguisher :1:27 is the route distinguisher there. :152.12.4.0/24. Next hop is equal to PE1. And what is the route targets and what is the label value. Now this is the information that PE1 is advertising to PE2 as a part of VPN v4 route exchange. Now PE2 would install that particular route into the VRF table which is associated to CE2. Now somehow we were able to get this particular prefix reach all the way from PE1 to PE2 via the MP-BGP. Now the information that PE2 got and installed in the VRF table, since I'm already running a routing protocol between PE2 and CE2, whatever it may be, BGP or static or REP, that particular prefixes are now advertised to CE2. So this way, CE2 knows how to get to CE1 from a control plane perspective, or from a manner where I know how to get to CE2 now, it's a matter of forwarding the traffic. So this particular slide kind of walks through that, and it kind of gives us a view as how I will be able to forward this if I have a packet that I need to reach CE1. So 152.12.4.6 as an example is a packet that I'm sending from CE2, and that packet comes to PE2. So PE2 already has this particular prefix information in the routing table. So it does a lookup on this particular packet, and now the lookup is done in the VRF table, and that would give the information to PE2 that to reach 152.12.4.6, your next hop is PE1, because that is already I installed as a part of my, in the control plane operation as I explained. The next hop information which we are sending here as PE1, that's what PE2 also knows. So PE2 would, once the lookup tells him that, okay, the packet is supposed to go to PE1. Now, next step would be is I need to encapsulate this packet, or what we call as I need to rewrite this particular packet once it is supposed to be forwarded to my uplink. Now that is where is that rewrite information I am talking here. So where we are referring to, this is the packet 152.12.4.6. This is the packet, and I'm encapsulating this packet. So what are the things I'm encapsulating? So the label, this is the 29 is the label that I had obtained from my previous control plane operation slides that I had explained. So there I have a 29 as the label that PE1 had provided. So that is the label I'm imposing. Along with that, I'm imposing two other things. One is the L2TP-v3 header, and this is the regular IPv4 header. Now, this is the packet that would be traversing in my core, and once it comes to PE2, now the lookup is done only on this top header, which is my IPv4 header. Now, this is a regular IPv4 20 byte. So what that would tell is, okay, so you need to, the source IP address of that is PE2, destination IP address of this is PE1. So the P router just does a lookup, and through IGP, he already knows how to get to PE1, because that's the next hop is P1. So this entire packet, based on the IP lookup that it did on this, it will forward them as it is. So only change here, there is no change from P2 perspective. All he did was a lookup on this and forwarded the packet to P1. Now at P1, he does a lookup. It says source IP address is PE2, destination IP address is PE1. I need to forward it to the next hop, which is PE1. Now the packet that comes here is this, the whole thing comes, which is your IP, that's the tunnel IP, and then you will have the VPN label. Now the lookup here would be done on this IP packet, the first lookup, and that lookup tells that the packet belongs to PE1 itself, because the source IP address is matching to PE2, and session ID address, the destination IP address is matching PE1. So this lookup now tells that packet belongs to PE1 itself. So the next step, as I explained earlier, the next step is to go and check what is the session ID and the cookie information for this. So that is what this diagram is referring to. So if the session ID and cookie values is what it had obtained from PE2, so it does a match on it, and if there is a match, the packet is further is subjected to lookup. If it doesn't match, it's going to drop that packet. So the lookup is done next onto the VPN label. So this is the label that PE1 had allocated and which was forwarded to PE2. So PE1 now does a lookup on the label, and that would in turn indicate that the outgoing interface for this particular packet belongs to this link. So now I would remove the label that I had allocated previously, and now I forward the regular IP packet. So this is the pretty much flow from a CE2 to CE1. And this is the same operation that would be involved if I have thousands of sites which are terminating to PE1 and thousands of sites which are terminating to PE2. The same process would be involved for every packet that leaves from a particular PE going towards the particular CE routers. Okay, so this was a quick view in terms of how an L3 VPN for V4 is pretty much done using IP as a core. Now, the same concept would still hold good if I have same services I want to enable for V6. In the sense, instead of having an IPv4 addresses or IPv4 services that are enabled between PE2 and CE2, I would like to have IPv6 here. So this is an IPv6 cloud. This is another IPv6 cloud for the same customer. So that means this CE2, which was having a link to this, today would like to enable IPv6 services. All along it was providing V4 services, and I would like to have V6 services as well. Now, if that needs to be done, what are the changes that are involved in my service provider network, or what are the changes that are involved from PE2 to CE2 is what the further slides talk about. But one thing to keep in mind is from a service provider perspective, we would like to see that it's transparent. We don't want to have an additional overhead of doing any changes in my core routers to handle these IPv6 packets that would be coming, or I don't want to now switch from my IP core that existed. I don't want to switch to some other technology. So I would like to still use the IP core that I have, and then I should be able to transparently forward the IPv6 traffic or the prefixes that I receive from each of these sites across this network. That's the first requirement. So that means the core should be transparent for this. And the second thing would be is all the services that I was giving on this particular link for V4. So it could be a multicast service, or it could be any of the QoS features that I had provided. All of that should still hold good. Means I don't want to make any changes in my network with respect to all the services that I was providing to my customer who was home to this link. So that pretty much tells us that the PE2 or these PE1s have to be V6 capable. Means they should be capable of handling V6 that's coming in. That's one requirement. And at the same time, the core router should never be dealing with IPv6. And I don't want to change any of my technologies or any of my configuration that exists in my core routers. So with that in mind, so we'll go through the few other slides which talks about how this V6 is capable, how we can transport the V6 prefixes from one endpoint to the other endpoint. So this is what we talk about 6VPE. So it's one of kind of the terminologies that folks use, but there are different ways to look at it. They would have called it in a simple way, but we know PE means once we say PE, we always consider as a provider edge router, but we are calling it as a 6VPE. It could have been V6PE, right? So we always call V6, so it could have been a V6PE, but the nomenclature is said as 6VPE. So all this is referring here is it's L3 VPN services for V6. So how we have been providing all along V4 services, L3 VPN V4 services, now the same thing we are going to provide for V6. So that's what it is called as 6VPE. So the provider edge router, which is capable of providing V6 services, is a 6VPE router. There are multiple approaches for transporting V6 over V4 core, but this is not talking with respect to L3 VPN. So these bullets are referring how I can transport V6 over the V4 core. I think we had a lot of discussions in the morning in our sessions where we talk about tunneling mechanisms and things like that. So this slide kind of gives a quick capture of it. where it is talking about how I can transport V6 over. If I have an L3VPN services, I can easily transport a V6 network. Or if I have a L2TP-V3, L2VPN services enabled, I can transport V6 on it. Or the V6 over V4 tunnels, I think we discussed that in that session. But the key things, the last 2 bullets is what I am referring as a part of this discussion, is how I can achieve L3VPN services using the same IP core. And so it comes under 2 categories. One, we call it as 6VPE, which is L3VPN V6 services, and the other one is a 6PE. So a slight variation to the 6VPE here is the 6PE kind of provides the similar kind of services, but only difference is the customer prefixes, or the customers who are terminated to the PE routers are not a part of any VRF table. Means we can call it as an V6 Internet Access services is what the 6PE boils down to. So V6 global prefixes are now is in the PE routers, and that's what is being forwarded. So 6VPE is where enterprise customers are terminated onto a provider edge router. They are a part of a VRF table, and V6 prefixes are present in it. So from a featured overview here, so L3VPN services for V6 VPN customers, this is what I indicated, and there is an RFC which kind of talks about this. So 4659 is kind of giving in detail about what extensions that we have done to our regular L3VPN. So L3VPN extensions done in terms of mainly with respect to BGP, because we have added a new address family today, which is what we call VPN V6 address family. So for V4, we had VPN V4 address family as part of this exchange. Now for V6, we have added a new extension which is called VPN V6. The core can be MPLS or IP, as we have discussed, and this session is mainly focusing on the IP core part of it. No dual stacking in the core. I think this is the most important part, because we never want any changes in the provider network. All the infrastructure investment has been done to make sure that I don't want to keep adding more stuff to the already existing P router, so I would like to be as transparent as possible. So there is no V6 in the core, and feature functionality in parity with V4. So the not only from a configuration perspective or for enabling these services, pretty much from a network management perspective, or any of the additional features that I'm going to enable on top of this should be transparent. So I really don't want to have a new set of protocols that have been defined just to provide V6 VPNs. So feature functionality have to be in parity with what we already provide. So this is one of the common demands that any service provider would give, because customers are already used to some of the services that they have got for V4. So they would like to see the same thing available for V6 as well. So V6 L3VPN should be offered over the same V4 L3VPN infrastructure. So this is where the dual stacking comes into picture. So what that basically means is from a provider edge router to the customer edge router, I would have had an access, which is what I have enabled V4, and I'm providing V4 services to it. Now tomorrow, if I want to provide V6, don't ask me to come with another access to me. So I would like to use the same access that I have been provided, and I would like to have all the services which I have on V4 similarly on V6. So it talks in terms of I would like to have E-BGP as a routing protocol that I have been using all along for my PE to CE. I would like to still continue to use the same. Either a new session for V6 is fine, or the best is I still want to use the same V4 session which I was using for V4 addresses, I would like to still continue to use for V6. So things like that is what the demand is, and that's what I think most of the vendors are making sure that the V6 services, enabling V6 L3VPN services, is as much transparent as possible from an end user perspective. And there are some challenges in terms of it, but most of the vendors do provide the 6VPE functionality very well today. Okay, so this is this kind of gives a complete picture as what I was talking about. So if you look at it, this is the service provider core who would like to offer V6 VPN services, or who is already offering V4 services today. Now there are P routers, and these are the PE routers that are existing, and this could be the IP core. So similar to what we discussed earlier. Now these are the customers. So this is one customer, V6 only. These are the V6 only customers, this is a VPN yellow, and there is a VPN blue. So these are, we can call it as two customers. So this particular customer, which is in VPN blue, would like to have V4 and V6 VPNs on the same link. And similarly, there is a customer here, which is an yellow customer, who would like to have only V6 services. Now, there is iBGP sessions that are running across these PE routers, which is the regular multi-protocol BGP sessions that run. Now, what are the things that have been modified with respect to BGP? I think some of the slides further talk about what is the role of BGP here, which is giving us a flexibility in making this transparent. Means there is no changes anywhere. I'm just making changes in the BGP configuration or the BGP options. So 6VPE so kind of talks about here is it's an implementation of this, and then there is a VPN v6 address. So VPN v6 address family is what is the new thing that is provided by BGP. So the prefixes that I'm learning from the customer, so for example, from this v6 only customer, I'm learning a v6 prefixes. Now this v6 prefixes, when it is supposed to be forwarded to this particular PE router, it will be modified or prepended with some specific values, which makes it as an VPN v6 prefixes. Now those values are pretty much the same as what we had in the case of v4, where we are including a 64-bit route distinguisher. So this is the same route distinguisher that we used in the case of v4 also, and 128-bit IPv6 address. So we'll see this a little bit in detail in the next further slides. Next hop is carried as a v4 mapped v6 address. I think if you had attended the ARIN sessions there, so we were talking about different types of v6 addresses. So in this case, the key thing to note is PE1 and PE2s, these PEs are not changing their loopback addresses. So the loopback addresses here are the common parameter that we use for peering between PE1 and PE2, as we do in the case of v4 VPNs. So I would like to still use my v4 IP addresses that I have defined on those loopback addresses, and would still continue to use the multi-protocol BGP session. But I would like to carry now v6 prefixes. So if I carry the v6 prefixes as it is, the next hop information that this PE gets will be pointing to a v4 address. So this PE would not be in a position to make a call saying, I got a v6 prefix, but the next hop is pointing to a v4 address. So it will not be able to resolve this particular prefix or install this particular prefix. So there has to be some mechanism where the v6 prefixes that I have learned from my customer, when I'm forwarding them to this remote PE, has some kind of a translation or a conversion. Now that's what this VPN v6 does for us. So VPN v6 is making it is unique by putting the route distinguisher, by prepending the route distinguisher, and then the next hop information for that prefix is basically, it's a v4 prefix still, it's a v4 mapped v6 prefix. So I have a details on how that would look. So basically I'm using the loopback address of this particular PE and prepending it with this, making it as a unique v4 mapped v6 prefix. The changes, additional changes that we have done in VPN v6 as a part of multi-protocol BGP extension is we are coming up with, we have a new address family identifier, so which is with 2. So one is what we use for v4, and sub-address family is VPN 128. So this sub-address family still remains the same what I use for v4 VPNs. I'm still using the same for v6 VPNs. Only change to recognize a prefix as this is a VPN v6 prefix and not a VPN v4 prefix is by making a changes in the address family. So the prefixes that I'm learning now will be having an EFI with 2. Now, along with this, so this is the concept I was talking about, is encoding of the BGP next hop. So if you refer through that RFC, they talk in detail about encoding the BGP next hop. So what basically that means is I need to take the v6 prefixes that I learned from the remote PEs, and now I need to convert them to make it as v4 mapped v6 addresses. So that is what is the encoding that needs to happen. So I did discuss a little bit on this. So the key main differences to make this as transparent as possible to the end user is changes in the multi-protocol iBGP. Now this is the key changes which is making the whole experience of adding v6 into this network very transparent. So from a service provider perspective, all the only change that he should be mainly aware of from the core, from the provider edge router perspective, is only making changes in his BGP configuration. So now the BGP configuration which he had been using all along had included, you could have seen in the routers, address family VPN v4. Now that, along with that, he will be adding what is called as address family VPN v6. Now the moment he enables that between all his PEs, these PEs are now capable of exchanging v6 prefixes. That is the first thing that would have happened. Now at the same time, the edge links between PE and CE, they should be dual stack, means then they should be able to handle v4 and v6. So what this gives us here by making this particular iBGP session to carry VPN v6, now I can exchange the label IPv6, labeled IPv6 VPN prefixes. So CE would have advertised a prefix to PE1, and PE1 advertises the prefix to PE2. Now those prefixes are VPN v6 prefixes, so obviously I need a label, which is what I can map it to that particular prefix. That can only be possible because now the multi-protocol BGP has extended to handle it. So I think the next bullets kind of talk about it. The changes is only adding an address family VPN, and he's having the regular IP only change now, the changes are these. So what changes I need on our case work? Because even before address family capability exchange. Now the new thing that I need to do is something else. So the route reflector should be capable of handling these. So I'm going to be now there are maybe other than we still have IP4 services. We can have one reflector as a point of failure. Only for VPN v4 have a router reflector. So this is a slide in terms of talking about the exact flow here. So these are the key routers which are doing for services also. So assume they are no so key routers are so from this particular P1, C1, P2, so the router. Now, before that, I know how C1 and P2 here. So I know that I have P1, C. BGP is already IP4, so that's already there. So this part is already taken care of. So now that I'm going to have consider. So this is the packet in this part. And I will do that. I will have this and even an AP packet that goes out with an L2TPv3 header. So I take it on as well. Now I have some here would like to have a v6 services. Now we have here. So those now that changed between this particular C as a E and we have these prefixes, once I get them into the VRF table or the routing tables, obviously there will be a regular mechanism of forwarding these prefixes or advertising these prefixes via my MP-BGP. Now, this is what this particular bullet is referring here. So the PE router receives this IPv6 advertisements from the CE router. Now the PE router installs these routes in the VRF table and assigns a VPN label attached to that particular prefix. So here I just wanted to explain one thing here is the VRF table or the VRF definitions that I have done for my V4 today, which is already up and running for this particular customer. I'm adding an additional information which is called an address family IPv6. So I was having a VRF which had an RD value, which has the RT values. I hope you guys are aware of the route distinguisher and route targets. So the route distinguisher and route targets that I used for V4 customer for the V4 VRF, I'm going to maintain the same thing. All I'm doing is I'm adding an additional address family IPv6 and I'm putting the RTs for it. That is the change that I'm doing for the VRF. I don't need to change anything in the RD for that VRF. I can reuse the same RD and I'm reusing the same interface. All I'm doing between this PE and this CE that exists here, I'm defining IP addresses for V6 and I'm running a routing protocol between PE and CE. These are the two things that I'm doing to get the prefixes installed into this particular VRF table. Now, from a separation perspective, the routing tables would be separate, right? So we would have a V6 VRF table and a V4 VRF table for the same customer link. So you wouldn't be finding one single table for WRF 1 and put both these prefixes together, because from a you need to keep that as independent as possible, because you don't want to put both these prefixes into the one table, right? So the PE router installs these routes into the WRF table and assigns a VPN label attached to the prefix. So this is the regular MP-BGP. There is nothing uniqueness that is being done here. So since I have multi-protocol BGP and I have VPN v6 address family capabilities exchange, so any prefixes that I learn from my customer router, I need to allocate a label for it. So that is the VPN v6. Because of the VPN v6, I'm making this particular prefix with label. So what that means is he allocates, this particular PE router allocates a label. Now this particular label is what I'm exchanging as a part of multi-protocol BGP to the remote PE. Now this particular bullet here is what that is referring to. So this I already explained. The PE router has a VPN v6 address family enabled and peers with the remote PE router. So this part we already had done it before. So the prefixes that I got here, now I need to advertise. So as a part of this advertisement, what is the key factor that I need to keep in mind? So the VPN v6, that BGP encoding which I was referring earlier, is what this is. So this is the v4 mapped v6 addresses. So the v4 mapped v6 address is as defined as a standard. So this is the format that you would see any of the v4 mapped v6 addresses looks like. So the prefixes that I'm advertising from this particular PE router to this particular PE router is going to go with this as the next stop. So that means : FFFF : this IPv4 is nothing but the loopback ID of this particular PE router. So now this particular prefixes once it reaches the remote PE. Now he would install this particular PE based on the RD and the RT values that he had already defined for this particular VRF. So he would install this into the BGP table as well as into the VRF tables. Now further, once he has this particular routes, the forwarding these routes to the corresponding CE router is again based on the routing protocol that I run between PE and CE. So if I'm running a BGP again from my iBGP prefixes that I got, I would have forwarded to the customer's routers. Or if I'm running say EHRP, I would have to redistribute those routes that I have learned from there and forward it. Or I'm already running a routing protocol between these two, so the routes would automatically reach the remote CE router. Now this kind of a flow is what typically happens for v6 prefixes. Now in the same network, to do the v4, it's pretty much transparent. So you instead of v6 prefixes, you would have got a v4, and it would have become a VPN v4, and it would have reached the remote endpoint. So from the same access, I'm able to enable both the services. Okay. So from a forwarding perspective, so this is how it would look like. So before from the forwarding, let me give you a little bit background on how these prefixes have been learned. So here is two sites. So VPN B, VPN B. These are the same customers but different sites. So CE1 is advertising prefix PE1, and now from PE1 we would be going to P1 or P2 or PE2. This is my core. Now the prefixes in this case, the prefixes were advertised. So VPN B is having, I think, instead of the IPv4, it could be the IPv6 prefix here. So IPv6 prefixes from CE1 is advertised to PE1. Now these prefixes would have gone to PE2 as a part of the regular VPN v6 exchange that I explained earlier. So this prefix now is advertised back to CE2 as a part of running protocols, whatever I'm running between these two. So now CE2 knows how to get to CE1 as a part of this route exchange. Now from CE2, I will be sending a packet for this particular destination, which is 2001::1. Right? So now this particular packet, when it reaches PE2, a couple of things that would happen here is it will be imposing a label 29 as an example. So this is the label that I had exchanged as a part of my VPN v6 address family exchange. So from PE1 to PE2, I would have done this route exchange. So I will be imposing that particular label 29 on this, so which is what I call the encapsulation here. Now from here, the packet that is supposed to go out, now two things that needs to happen. So one of them is I need to impose, or I need to encapsulate this particular packet with an IPv4 header and a L2TPv3 header. So this is the part that was already done before. Means PE1 knows how to get to PE2 and what encapsulation it is supposed to impose. So that part have already been done for V4. Now I'm going to use the same concept here, but only the payload is different. So the payload is a V6 payload. So I have a V6 payload here, VPN label for that particular, but the source IP and the destination IP, which is part of this IP header, is just belonging to PE1. So the source IP address is PE1, PE2, destination IP address is PE1. Now once this packet comes to P2, only lookup is done on this IPv4 header. Now the remaining all of this is transparent. So the packet that comes to P2, it would do a lookup, and then it forwards that particular packet to PE1 because it's a regular IGP or a regular IP lookup. Now from P1, the packet would be forwarded to PE1, and which is where you would see a couple of things needs to happen. Here is where he would do a lookup on IP header, and that lookup will give an indication that that packet belongs to PE1. It then does a lookup into the L2TP-v3 header, does the session ID and cookie match, and then a label lookup. So once the label lookup is done, then it will figure out that this particular packet is now supposed to be going out onto VPN B or CE1. Now the lookup is done for this particular prefix 2000:11. So this particular IPv6 prefix is done into the V6 BRF table. So this importing of this prefix and the prefix available in PE1 and all this was already done as a part of the regular control plane setup. Now the packet from PE1 would be forwarded to CE1, regular IPv6 forwarding. So a few things here, this source address, destination address, and the data is pretty much for VPN v6, pretty much for the IPv6 prefix for this particular customer's payload. VPN label is what was exchanged. Session ID and cookie information is what was exchanged as a part of my tunnel or an L2TP-v3. And then source address and destination address is what this is the exchanged as a part of going from PE1 to PE2. So this is how it would look when I'm looking at a packet at this place, because encapsulation is happening at this point of time, right? So any questions on this? Okay. So this is just one of the slides that I just wanted to bring up, and which talks about global V6 services. So here, so when I'm calling it as a 6PE, if you look at the key differences here is this is regular MP-BGP sessions that is running. It's still the same IP core. Only difference here is this particular PE router is having V4 as well as V6, and this is not a part of any VPN. So it's a globally defined IPv6 addresses, which is a part, and each one of these V6 links or V6 sites have unique V6 addresses, because you cannot have overlapping V6 addresses now. The reason being they are not as a part of any BRF tables. So IPv6 global connective over IPv4 core. So it's still the same. There is no much difference. I could still use the same tunnel encaps and L2TP-v3 formats that I'm using, as transparent as possible. And then IPv6 reachability is exchanged via PEs, via IBGP, that still holds good. IPv6 transported from 6PE to 6PE. So from here to here, the V6 prefixes would be now regularly transferred. So there is, even now here also, the P routers are not aware of any V6, because IBGP session is the one that had carried these IPv6 across from PE1 to PE2. Okay, so just to give you a little bit as I said, this is just a sample flow, because pretty much I assume that basic L3VPN concepts are known, and here all I'm focusing more with respect to how all of this are integrated, whether it's a IP core, an MPLS core, and how I can enable V4 and V6 services as transparently as possible. So looking at this particular topology, you could see that a PE1 and PE2 are the two provider routers, and they have these are the customer edge routers. So I'm just calling it as router testers as an example, but these can be assumed to be my edge routers. So I am running, these are the access points that I have. So this has some POS links, or it can be a GIGI link, or it can be any of the interface types available from PE1 to this router tester. And from PE1 to PE2, I am having an uplink using it's a POS uplink that runs from PE1 and PE2. And if you look at the loopback addresses, these are the v4 loopback address here, 555, it's a /32 and 333 on my another /32. Now I'm running ISIS in my core, or I can go with OSPF as well to achieve the reachability between PE1 and PE2. And I'm running IBGP session, which runs from PE1 and PE2. And this IBGP session is having capability exchanges for VPN v4, for a tunnel exchange, tunnel information exchange, and VPN v6. So this is the key part to this, because if a provider doesn't have a VPN v6 address family, then he will not be able to provide v6 services. He will not be able to have 6 VPE or v6 services for its customers. So pretty much PE1 and PE2 have to have at least these to make sure that they will be able to forward v4 or v6 over an IP core. Along with this, from PE2 to my router testers or my edge routers, I would be pretty much having the regular routing protocol. So it could be eBGP or OSPF or static routing. So here I'm just giving an example of eBGP that runs between my CE routers and PE routers, and the same between here. So the prefixes that are advertised here, I'm giving one example as 120.110. So it could be any other prefixes that I'm advertising, which goes from PE1 and PE2. Now, so the few configurations that one has to make this work here is configuring the multi-protocol BGP with this, configuring ISIS for this, and a tunnel template or a tunnel configurations that needs to be done on this particular router. So once this is done, then we are eligible to accept prefixes that come from the CE routers, and then we will be able to forward those prefixes to the remote CE routers. And when the traffic needs to be coming from this particular CE router all the way, if it has to reach to the CE router, then the encapsulation with L2TP v3 and things like that will be pretty straightforward. So this is, again, as I said, this is a config guide, which kind of taken from iOS XR. 12.2s iOS is capable of providing VPN v6. 12.4t, some of the platforms from iOS, from a Cisco background, I'm saying that it is capable of providing v6 services. While XR, I'm not sure how familiar you folks are with the releases on XR. One of the releases, which we call release 3.5 in iOS XR, and 3.6 is those releases are the ones that are capable of providing this VPN v4 or VPN v6 capabilities. So pretty much this configuration, what it is referring is derived from VPN v4 and VPN v6, derived from iOS XR config guide. So PE1 config. So looking back to this, so this particular PE1 router is what would look something like this. So I'm just picking one of the 1808, one of the service providers routers here. So BGP router ID, I think we spoke a lot in the morning as well. So the BGP router ID is a key. It's very essential in the case of XR. It's not explicitly there, then it will not be able to figure out what will be the router ID to pick. So it's IPv4 loopback address that I have defined is what I'm going to use the router ID for, irrespective of whichever address families that I'm using here. So we discussed about v4 map v6 addresses. So it will generate that address based on this loopback ID. So it will be : FFFF : 5.5.5.5.5. So this router ID kind of determines for all the parameters that we have defined here. Now, neighbor 333. So this is the neighbor that I'm talking with, and I'm giving an update source loopback 0. This is the regular IBGP concepts. Address family IPv4, tunnel, VPN v4, VPN unicast. So each one of them has its own has its own needs, and the capability exchange that I'm done between these two will be capable of doing few things. So for example, if with this IPv4 tunnel, this address family is going to help forward the L2TP v3 information between PE1 and PE2. So once I have defined the tunnel template, I will be able to forward once I have defined the tunnel template, I will be able to forward the session ID and cookie information from PE1 back to PE2 and vice versa. VPN v4 unicast, this one makes every customer prefix unique across the network, and I'm exchanging this between PE1 and PE2, and I'm making it unique by prepending with RD values and things like that. VPN v6, so IPv6 unicast, this becomes essential if I'm doing the 6 PE services. So I am making IPv6 prefixes unique again by using the IPv6 unicast. VPN v6 unicast for the 6 VPE services, this is essential because I'm making the customer IPv6 prefixes unique across the service provider network, right? So pretty much all of them will make my IBGP session carry any of these services. Now, if I want to add more to it, for example, I would like to have multicast along with this, which is the same customer link, which is carrying v4, carrying v6. Now I'm going to get v4 multicast traffic that is coming in onto the same link. What is the additional thing that I need to do? So you will be able to modify the router BGP configuration to support address family MDT or address family multicast. So from the same IP core that I'm having, I'm able to transport all of these services on the same infrastructure. Pretty much same infrastructure for any of the services in future also, which gets enabled. Because I'm relying on BGP extensions, and as you know, a lot of peaks believe in BGP for carrying all of this. So pretty much relying on BGP for my capability for the exchange of these services, it helps from the service provider that I'm not investing anything in my core network. I'm just using the same infrastructure that I have. So pretty much this kind of gives a view of how the BGP would look like. From a PE to CE, so this is again from XR. I didn't say this, I'll fix this. So this is again from an XR, iOS XR. So if you look at, this is PE1, and this is the interface that is talking to the route tester or the customer or the CE router. So this is where my services are enabled. So this is what I would have provisioned to my customer, my enterprise customer. This customer belongs to VRF VPN 55. This is the name of the VPN. It can be anything. This is the IPv4 address I have given for that customer. And this is the IPv6 address which has been associated to that particular customer or the link. I'm telling that IPv6 is enabled on this. So this is an optional command. By just defining IPv6 address, I think IPv6 do get enabled on the interface. Encapsulation is HDLC and keep alive disabled. So I think this is generic. So along with this, the other thing which is associated to this customer VRF VPN 55 is this part is used with respect to VPN v4 or v4 services or IPv4 services. So address family, IPv4 unicast, route import target, route export targets, address family IPv6 unicast. This one I'm using the same RT and RD. So this is what you might hear elsewhere, people calling it as dual stack VRFs or dual stack VRFs. So dual stack VRFs basically mean that is a VRF which I'm using for v4. Now the same VRF is now capable of making it as a v6. So from a service provider perspective, the only additional service component or service provisioning component that is involved here is making sure that I define v6 addresses on the same existing v4 interface that I had before, and I'm making this particular VRF a dual stack VRF. So these are the two changes from service provider provisioning. And now from a routing protocol perspective, this router BGP VRF VPN v55, so what this, I think it's a snapshot from a config. What this tells here is I am looking for VRF VPN v5 and I'm running eBGP between my PE and CE. Now, the way I look at it, so I have the RD defined under VRF, and this neighbor 15112 is where I'm talking with my customer. This is 15111 is my local router. 15112 is my CE router, and his AS is 7000. Address family IPv4, so these are the route policies to accept or deny routes. And neighbor 1511:2, this is the neighbor address. Remote AS is 7001. It could be the same. It could be different. He could have two links, or it could be the same. And address family IPv6 unicast. So pretty much now by doing this, the PE to CE links will be capable of exchanging v4 prefixes or v6 prefixes. And now we will be able to import them as an address family VPN v6 because I already have the VPN v6 capability exchange done previously. So any prefixes that I learned from this particular customer will now become a VPN v6 and gets forwarded to the remote PE router. So the changes that are involved, looking at it from a high level, is provisioning involves only these few steps, as well as whatever is the routing protocol that I have chosen. Here I have chosen BGP for v6, if I had used EAGRP or if I had used OSPF v3, then my configuration would be under OSPF v3 for that particular VRF. Okay, so this, I think this kind of summarizes all the possible scenarios that one can achieve v4, v6, or L3VPN services. Now, on top of this, I could have included many other things, but it's a huge list because we could have L3VPN on the same existing infrastructure. So I am having the IP infrastructure with providing v4 and v6 L3VPN services today. Now, new services can be offered transparently. Now, that could be layer 2. So I'm already running L2TP v3. I can use the same L2TP protocol that exists and achieve layer 2 VPNs, so which is already being serviced and provided today. Now, on top of this, I could go with native multicast, or I can go with multicast VPN. Now, if I want to offer multicast VPN services, BGP MDT SAFE. So this is the subaddress family under BGP again. So there is a multi-protocol BGP has extended to support multicast VPN also. So how they do it is basically we have an MDT SAFE that is defined. So in my router configuration here, it would have become address family MDT unicast, address family MDT multicast. Right, so things like that can be enabled as well. So quality of service is another parameter. So from an edge and core, I think it's very much transparent. So I didn't mention one of the thoughts there is the tunnel IP, the IP which is carried as a part of L2TP3 header. It's a 20 byte IP, and you saw a toss byte there. So that toss byte again can be used for any QoS related stuff that I want to do in the core. So similarly, how we have when we have an IGP label in MPLS, where we have the EXP values which are used in the core to do all the quality of services, the same functionality can be obtained by using the toss values that exist in the L2TP v3 header. So that's what I meant here. It's transparent. I can do edge as well as core quality of service, and so all these features can be integrated on the service provider network, and which is very much transparent to the customers, right? Okay, so CSE and inter-AS, I'm just keeping a bullet here. Let me give you a 2-minute talk on this. So CSE and inter-AS, I hope some of you are aware of this. So basically, this provides a functionality of interoperating with the other providers. So I could have my customer who is home to, I'm giving examples here, so a customer who is home to AT&T, who is offering L3VPN services, but I have my site, another site is home to another provider, it could be Sprint. So now, how can I achieve connectivity between AT&T, so the site which is connected to AT&T and a site which is connected to Sprint? So there has to be some mechanism of interoperability or service provider route exchange between provider 1 and provider 2. So this is where the carrier comes into play, or inter-AS comes into play. So inter-AS is pretty much used in the scenario which I explained, where I have multiple options. I could have inter-AS option 10A. It's one of the options of connecting these verbs back to back. Or there are many other options like 10B and 10C, which kind of provides different mechanism of forwarding prefixes or customers, or providing connectivity of customers who is home to site 1 on one provider, on a site on another provider. CSE is basically a service provider 1 is using another service provider as a transit and reaching the third service provider. So I could have provider 1, provider 2, and then I have the main provider or the transit provider. So carrier servicing carriers, so supporting carriers. So these two concepts or features or functionality which is so critical is pretty much transparent, whether it's IP core or MPLS core. So today we have that flexibility already in place, which can provide CSE and inter-AS functionality, which is in parity with MPLS-based core. Transit carriers can be IP core based, while baby carriers could be MPLS core based. So what I meant in the case of CSE is you have provider 1, provider 2. Provider 1 can be MPLS based. Provider 2 can be IP based. So it's still, both of them can work transparently. That's what this talks about. So in summary, as if there is an infrastructure which is full of IP core, and there is no investment, or there is no plans to go with the MPLS-based core, we have mechanisms in place today where all the business enterprise services can be transparently enabled even though I have an IP core. enabling L3VPN, V4, V6 over the legacy infrastructure. I think that's what brings in as an advantage here, because there is no investment in the core to make any changes. Or I have an IP core which I've been using all along. I need to add these additional services because my customers are demanding. It's still a feasible thing. New services can be safely integrated easily. The integration is pretty straightforward because we are relying on BGP for most of it. I don't believe this part, but I did put it. Network troubleshooting and maintenance is simplified. I don't think so. I don't think so. Any day we are in a position to call anything is simplified these days. So only one thing which I learned over the period of time is going with an MPLS background. There is a cell-based MPLS, if you all know about, which is based on ATM network. If I have an ATM infrastructure, I want to run MPLS on it, so we call it a cell-based MPLS. So the complexities that involved in the cell-based MPLS and the MPLS in general, from an expertise perspective, I think that is what this is going to solve, because IP is something that we are all comfortable with. And pretty much the features are parity with MPLS, so you wouldn't see any difference in terms of whether I have an MPLS core or an IP core. As a vendor, implementation of the gears are very much simplified. So from a lookup perspective, from configuring my hardware or designing my hardware, they have been made things which are very much simplified because routers are good doing and route lookup, IP lookup. So that's the, I hope this session gave you some overview about how we can use IP core. If you have any questions, please let me know, and I'm getting a ding on time's up. So any questions? So I have my email ID on it, and I'll be around. Please feel free to discuss. I've been so one of the key providers who are doing this already. Sprint is one of the key providers who are offering this kind of services today. It's been pretty much going well. So I can share a lot of details with their deployments and how it's coming along. Okay. Thank you.